So we're doing some few practice problems and giving you some more formulas and whatnot. Let's go ahead and look at this one right here. We've got the log of z times y cubed. What we're going to want to do is we're going to expand this out into a couple other logarithmic statements. Okay. So if you remember yesterday we talked about product rule of logs, the division rule or the quotient rule of logarithms, the power rule. Okay. And we also talked about the natural log of e. Anybody want to give me an idea how we could split up this problem right here into two log statements?
Log z.
I hear log z, and then what? Plus, I'm going to break it down one step before that. So log z plus the log of y cubed. That's based on the fact, if you remember, that the log of a times b can be split up into the log of a plus the log of b. So it's just an application where we're splitting things up, making things a little bit easier. One of the applications of this is in higher mathematics, when you have a very complicated problem. When you take the logarithm of it, then you can actually split it up, separate it out, and then deal with each part individually. In fact, my calculus class was doing that when we were solving some complex equations. We were trying to find the derivative. The first step in solving that was take the logarithm of both sides, because then you're able to split it up like this. Okay, so log of z, that's pretty much fine as is. Josie, what did you say? How can we simplify this statement right here?
You take the exponent and put the exponent.
Yep. Based on the property that we saw yesterday, if you have an exponent up here, you can actually bring that down as a coefficient. Those two things are exactly equal. The log of y cubed is the same thing as 3 times the log of y. And that was based on the property of exponents, because if you had a power to a power, then basically you multiplied that exponent here times the other power. So that's one of the things that we saw. We'll do one or two more problems splitting them up like this. Log of x over y to the 9th. So here we've got a division problem. Somebody else, if we have a division, log of a over b, does anybody remember?
Log x minus log y to the 9th.
Oh, y'all are jumping ahead. You're so fast. Here we go. That's right. If anytime you have a quotient, the log of a quotient, you can separate that out into log a minus log b. So, as y'all are saying, that's log of x minus log of y to the 9th. But then I heard mission over here. What'd you say for instead of log y to the 9th? Yeah, 9 log y, based once again on that power property. Okay? Alright, shall we try something a little more complicated? It's final answer right there, it's totally simplified. Let's look at this one. Log of x to the 7th times the square root of y squared z. That's a problem you might see on your homework assignment.
Wait, is the z outside of the square root?
It is actually inside.
Okay.
Good question. Now, does anybody remember how you can rewrite a square root as an exponent?
1 over, no.
1 over 2. Right, you can rewrite the square root as an exponent to the 1/2. So in other words, if you have the square root of a, that's the same thing as saying a to the 1/2 power. So the first thing that we're going to notice is that you have this term right here, x to the 7th, and then we've got this term right here, square root of y squared times z, that are multiplied by each other. Jesus, head up please.
Split the y up.
Yep, let's split it up here first. We'll split the first and the second part. So this is a product, so we can say log x to the 7th plus log, and if you wanted to, you could write the square root of y squared plus z, but I would recommend just Suji.
But it has to see in the.
Possibly. I'm just. Yeah, you could do that. Yeah, you could split it up into the square root of y squared. Yeah, you could. That's fine too. All right. So log of x to the 7th, can that be simplified
Yes.
into
7 log x.
7 log x plus
1/2 log.
Yep.
Y squared.
1/2 times the log of y squared z.
What if we distribute the 1/2 first?
Distribute the 1/2. Well, you can't distribute a 1/2 into.
No, before.
Okay, yeah, you could do that. You'll end up with the same answer. At this point, though, we notice we have a product, and that can be split up. So we've got 7 log x plus. Now this 1/2, you can think of it, that 1/2 is in front of all of it. So if I replace the log of y squared with the y squared z as the log of y squared plus the log of z, this is where you might make a mistake. You have to realize I've replaced this entire thing with this expression right here. As a result, I need to put brackets or parentheses around this new term of which I've substituted. So it's like there's a 1/2 times each one of those. So now I have 7 log x plus, I'm going to do two things at once. I'm going to distribute that 1/2, and at the same time, I'm going to rewrite log of y squared as 2 times the log of y. So plus 1/2 log z. And it just turns out that 1/2 and the 2 completely cancel each other out. Turns into 1 out in front. So you'd have 7 log x plus log y plus 1/2 log z. Okay. There's a lot of different variations on this problem. I think you've got 6 problems on the homework assignment. What's that?
Just that it.
Yep, that would be the final answer.
Right, couldn't you just like use the same way you're doing faster? Like if you take the root, like the y cancels out the square, so it just becomes y, and then the z is just gonna be like root z, and then you do like the same thing you're doing before. Except then, are you able to leave it as root z, or do you have to have?
No, I don't want any square roots or anything like that or exponents here. I want you to bring it out.
So is the square root of y squared times the square root of c the same thing as that?
Yeah, I mean, here's what you would have if do what y'all are suggesting. You would say, so we've got log of x to the 7th times the square root of y squared times the square root of z, right? Square root of y, all that's inside the logarithm. So that's the log of x to the 7th times y times z to the 1/2. So yeah, that would just be log of this plus the log of this plus the log of this, and then you could bring those exponents out. And you're probably pretty good at now bringing the exponents out at the same time. So you say that's 7 log x plus log y plus 1/2 log z. Right? I mean, you can just boom, 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 knock that out, no problem. Yeah, I just wanted to kind of show you step by step on some of those other things. And a lot of these, it's your choice, but if you continue the process all the way through and you're, using proper mathematics and those properties, then you'll get the right answer. I want to do another one that's going to be kind of weird. The log of the cube root of x times y to the fourth over z squared. Alright, first thing you should notice is that cube root, we can rewrite that as an exponent. Hey Zeus, how do we rewrite that cube root? 1 over 3, yep, that's as the exponent. That's the cube root means the same thing as to the 1/3 power. So now we're looking at this expression right here. Notice I've got a power. We can bring that power out to the front as a coefficient. So I have 1/3 the log of x y to the fourth over z squared. When you look at this, now what do you see is the biggest operation going on? The division. Yep. So now notice this 1/3 is out front, in front of everything. So I've got 1/3, and I'm going to say the log of the numerator, log x times y to the fourth, minus the log of the denominator, so z squared. The place where you might make a mistake is not realizing that you've got to put that whole entire term right here in brackets because we're substituting that for the log. So now we have 1/3, and notice we can split this term up. We have x times y to the fourth, so we could say log of x plus the log of y to the fourth minus, I have log of z squared, I'm going to bring that 2 out front, so I have 2 log of z. And I have a y to the fourth here in this middle term. I could bring that 4 out front. I'm going to do 2 things. I'm going to do that, and at the same time I'm going to distribute that 1/3 so that everything will be simplified. So I've got 1/3 log of x plus that 4 comes down, and it's multiplied that by that 1/3, so that's 4/3 log of y, or loggy, minus this 2's out front, and we're once again distributing that 1/3, so this is 2/3 log z, or as I say, log z. Has anybody tried these problems on the homework yet? A couple of you? Feel like you might do better at it now? Let me give you one more that's also something a little weird you may not be used to seeing. So that's the log of the cube root of x squared over x plus 8 to the 5th. Alright, now what do you see is the big thing going on inside this logarithmic expression?
Division.
Division. So that's the first thing we're going to break up. And identifying what the big operation is, that's a skill that you're going to need throughout the rest of mathematics education. So log of the numerator, so cube root of x squared, minus the log of the denominator, x plus 8 to the 5th. Alright, so we have the cube root of x squared. Once again, we will rewrite that as x squared and then to the 1/3 power. it is possible to do a little shortcut here. I'll show you that in a minute if you want to. This term over here, notice we have an exponent, so we're just going to bring that 5 out as a coefficient based on our property of logarithms. X plus 8 there inside. So anytime you have a power of a power, then you can multiply those powers. So this is log of x to the 2/3 minus 5 log x plus 8. Another common mistake students make, they look at that plus and they say, oh, I can split this up even more into log of x plus log of 8. And the answer is no, you can't. The only time you can split up a logarithm is if you have a product in here, if those are multiplied. If it's plus, too bad, so sad, you're stuck like this. The shortcut is, some of you may remember this from Algebra 2, you can go straight from the cube root of x squared, boom, right here to x to the 2/3, where, you know, whatever is in the numerator here, that's the numerator, and then this is the denominator. Okay? And then through power property, 2/3 log x minus 5 log of x plus 8. There are a lot of variations on these problems where you could have this in the numerator or in the denominator, or multiple things inside that square root. If I were to do every single problem, then I could spend 2 or 3 class periods doing that. So it's a little bit of an activity in can you solve a slightly different problem but still using these properties, okay? But you've got the rest of the week to take care of those problems. Okay? All right. So that's going to be pretty much it for properties of logarithms. There's a new formula, though, that we need to learn about. And that's called the change of base formula. Alright, so that's the title. This is the problem that mathematicians had way back when. They said, how do we solve mathematical situations where we have a base other than 10 or e? Because if you remember, those mathematics monks were out there doing all their calculations. They said, okay, 10 to this power is this, 10 to this power, 10 to the 1.5 is this, 10 to the 1.51 is this, 10 to the 1.52 is this, and they're going through making those tables. And all of a sudden now, someone has a problem that says, what's the log base 2 of 36? And those tables don't help you out at all because they're all dealing with base 10. And they also would make special additions with base e. But no one would go through base 2 or base 7 or any other base. Alright? So that was the problem that they dealt with. It also was a problem of students before they had these most recent calculators, because the older version, the previous version of these calculators did not have, in fact, if you have one of these, without the blue casing, it does not have that log base feature, okay? So students had to know this formula to be able to convert between logarithms. So here's where we're going to start. A to the y equals x. Go ahead and convert that exponential equation into logarithmic while I take attendance. Alright, just got that as a logarithmic expression here. Anybody?
Log base A x equals y.
That is correct. Okay. So, what I'm going to do is we're going to kind of take this, go through a couple different steps, and we're going to end up with a really cool formula that's going to help you find the log of any base. Alright? So, now I need you to believe me on this, and I can show you later if you need to. So what we do is we have some base A, which we don't know, and we'll raise it to the y power is going to give us x. No problem there. That's just our starting point. Here what I'm saying is that A can be represented as some other number raised to a power. Okay? So this is the principle here. For any real number A, we can write it as some number raised to another number. Let's see if you believe that. Mission, give me a number, any number.
667.
667. Okay. I bet you that we could find two numbers, probably find lots of numbers, that 667. I bet you we could find a number here and a number there that would match up to equal 667. Would you agree? In fact, I could almost give you any value b. I could say 6. All right. 667 is equal to 6 to the what power? I don't know. We've got calculators. Let's use them. What do y'all think? What's like 6 to the third? All right. 6 to the third is not 16.
216.
Oh, sorry. 216. Oh, more than that. What's 6 to the fourth?
1296.
1296. Oh, it's going to be somewhere between there. What's 6 to the 3.5?
529 and some.
529 and some change. Okay. Give me another value. 6 to the
3.7. Oh, no, that's children.
3.6.
6 to the 3.7 is
757 and change.
757. Too high. All right. So what's 6 to the 3.6?
632.
632. Now we're getting somewhere. All right. But you get the idea, right?
0.61.
Okay. So, do y'all see, just he gave me a number, I threw another number up there, we can find a number up here that would match it. Does that make sense? So, that's what this right here is saying. Is if I have any number A, I can find two other numbers that multiplied, one of them to the other power, then I could get A. That's all of that's saying.
It's 3.63.
3.63?
Ooh, I was right about to put that in. I was at 6.2.
Cool. Alright, so we're going to do a little bit of manipulation on here. So, if that's the case, alright, where A is equal to BC, then, we saw that A to the Y equals X. Thus, we could say B to the C to the Y equals X. See if that makes sense. So we've got A to the Y is equal to X. A is equal to B to the C, so therefore B to the C to the Y equals X. Make sense, Matthew?
Mm-hmm.
Alright, we'll keep going then. So what we know is that a power to a power, you can just multiply those. So B to the CY equals X. Power to power means multiply the powers. Alright, now what we're going to do is we're going to convert this exponential equation into a logarithmic equation. Katie, you're pretty good at that. Log base
B
mm-hmm.
times x
Yep.
equals CY.
Yep. Equals CY. All of these steps that we're doing may seem strange, but we'll get to something here at the end that's pretty cool, actually. So, given this, I'm going to solve for y. So y is equal to log base b of x divided by c. Alright? And, now that I mentioned that, my apologies, we should have also converted this one up here to a logarithmic expression. I'll have somebody else do this one for us. Clammy, can you convert this exponential equation into a logarithmic equation?
Log log base b times a, sorry, times a,
Okay, you say of a.
or of a, sorry, sorry.
Yeah, you're fine.
Equals
Equals
c.
c, perfect. So log base b of a equals c. Guys, you tune in here with us. Alright, so I'm going to do a substitution. I'm going to plug in this value right here for c. So we have y equals log base b of x over log base b of a. And then I'm going to say, all right, hey, look, we found y is equal to log base a of x. And I'm going to substitute that value in right here. So log of some base a, I don't care what it is, of x, that would be very more a-like, is equal to the log of some other base of x divided by the log of some other base of a. That's what's called the change of base formula. The idea is this a right here is some number that you don't normally have the log base of. So it's some number that's, it's not 10 or e. And then normally you choose for b, this is some base that you do know. Alright, so like all formulas, they really don't make a whole lot of sense until you practice it. Now I need you to pretend for a minute, gentlemen and ladies, that you don't have the log base feature on that calculator. Okay? So let's say you don't have, your calculator has no way of telling you what's the log base 2 of, I don't know, 25.
Put it into exponential.
And then you could put it in exponential and then do trial and error. 2 to the third is this, 2 to the fourth is this, 2 to the fifth, oh, that's 32, too high, so it must be 2 to the 4.1, 2 to the 4. You see what I'm saying? You have to play that little game. Or you change a base formula. Alright? 2 is the base that I don't know. That's my a value. What this says is I can take the log. Now what is a base that we do like?
10.
10. Log base 10 of x, of that number that I want to know, so 25, divided by log base 10, so I've got to match it, of 2, which was my a value. Alright, hey, that's easy, I have those on my calculator. Before there were calculators even, there was these things called slide rules that they had to use, so they had to use change of base formula because on the slide rule it only had base 10. So, somebody type in their calculator, log, you can just hit the log button, log 25 divided by log 2. Tell me what you get.
1.919, etc.
Do the whole thing, just do the whole expression.
1.9193302.
There's no way this is finally true.
Isn't it?
No, it's 4.64.
4.6 what?
It's
38.
Make sure you close your parentheses.
Okay, I didn't do
Uh,
Okay, that's why.
4.64. Alright, that seems to make sense. Let's check it out. What's 2 to the 4.64?
Maybe 4.93. So, 8
Okay. If we had more precision here, more accuracy rather, then we would be more accurate there. Okay. Now, just for fun, go ahead and let's try the log base formula now that if you have one of those fancy blue calculators, and just type that in exact. Log base where you can plug into 2, you can plug into 25 and hit enter. What do you get?
4.643856.
Yeah, you get the same thing. Okay. However, just you need to be able to have this formula for some of those homeworks. Okay. Oh, great, lots of time. Let's talk about what a logarithmic graph looks like. So y equals the log, we'll just say base 10 of x. Now let's go ahead and fill up some values here. All right. I don't know about you, my brain really doesn't work when I look in terms of like processing logarithms. If you turn it into an exponential, I can handle that, I can kind of get a feel for it all day long. But if I look at logarithms, I'm like, it's the other, no, I'm not really good on my toes thinking about logarithms. So let's convert this into an exponential so we can kind of see what x and y, where they are. All right, Kayla, you're up. Let's convert this to a logarithm or an exponential equation. No e. 10 is the base, which you've got right there, and y is the exponent. Yep. So you get the y up there. There you go. So x equals 10 to the y. All right. In this case, it might almost be better to start throwing in y values and seeing what happens with x. See what I'm saying? Like when y is 0. What's 10 to the 0? 1. When y is 1, what's 10 to the 1? 10. When y is 2, 10 squared, 100.
Gotcha.
When y is 3, we have 10 cubed, 1,000. Whoa. So let's think about what that graph looks like. So when x is 1, y is 0. So it's right there. When x is 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we go up 1. When x is 100, then we're up to 2. All right. When x is 1,000, so I'll use the full, so 10 times that, so like all the way over here. Then I'm up at 3. Are you seeing this? So we're like, is it a reverse exponential? Yes, it is. Excellent observation. It's an inverse exponential. Okay? So exponentials went, you know, as x got a little bit bigger, the y went shot up really fast. But with a logarithmic graph, x has to get really, really, really huge, and y just to make a little bit of a change, okay? But I need to figure out some values right down along here, like what's going on with this. Yeah, what happens if I, well,
What did you get with this?
can I plug in -1? If I have -1 equals 10 to the y, is there any y value that will turn this 10 into a negative? Like 10 to the what power? 10 to the, what's 10 to the -1?
1 over 10.
10 to the -1 is 1 over 10, so that's a 10. So, so when y is -1, we're like right here. He says it'll never cross. I challenge that. When y is -2, we have 10 to the -2. That's 1 over 10 squared. So that's 0.01. Okay, so -2, we're just even closer here.
Well, yeah, so it shouldn't.
That is correct. It never does cross the x-axis, or the y-axis rather. It kind of looks like.
Just gets really, really close.
Yep. There's actually, yeah, there's an asymptote right there. It gets really, really, really close. So, very similar to the exponential graph that we discussed last week, which looked like this.
And then never touch the x-axis.
Never touch the x-axis.
So it's like, yeah.
Okay, so let's talk domain and range of a logarithmic graph. Or at least y equals log base 10, okay? So the domain are possible x values that I can put in here.
0, positive infinity, right?
You might think so. I agree with the positive infinity.
Or is it positive infinity 0? Or wait.
Positive infinity is on the far end. I can go all the way over
Okay.
there, okay? I can continue on with the x values. And then the thing is, I do not have 0 as an allowable x.
Oh.
There's no y value here that I'm going to be able to take 10 and multiply it by itself to get 0.
So what is it?
So it's, I mean, I put a 0 right there, but I'm going to put this parentheses because that means I can't actually hit 0. Okay? So let me write it another way. Or we could say all reals greater than 0.
Oh, okay.
That's another way you put it. Now, if it happened to be all reals greater than or equal to 0, then the way I would write that would be bracket 0, comma, infinity parentheses.
Okay.
This symbol right here has meaning. It means you can actually hit that value. But in this case, we cannot actually hit that value, so it is not. So there's the domain, all reals greater than 0. What about the range?
Negative infinity to infinity.
You are correct, because we've got y values all the way down from negative. Now, are you telling me we're eventually going to hit 10 on the y value?
Yes.
Look at it, I carried this all the way out to 1,000, and I was only at 3.
Eventually.
Eventually, you would hit it. 10,000 would get you to 4. 100,000 would get you to 5. A million would get you to 6, and so on and so forth. But eventually, yeah, you'd get up there. It just would really take you a long time on that x-axis. Okay, so yes, all real numbers. So we could write that in set notation, negative infinity to positive infinity, or we could say all reals. Okay. By the way, the exponential and the logarithmic are inverse functions of each other. Okay? So e to the x and log base e of x are inverse functions of each other. If you remember what that means, that means that, you know, f of x, the function, starts off at the domain and points to the range. If you remember from your algebra 1 and your algebra 2, what does the inverse do?
Range to the domain.
Goes from the range back to the domain. And in fact, if you compare this domain and range with the domain and range of the exponential, you notice they're switched, okay? Because on the exponential graph, the domain was all real numbers. And what was the range? Anybody
0
remember?
to infinity.
0 to infinity, you can't, but not including 0.
Yeah.
So you see how they're switched, see how that works? Alright, so e to the x and log base e to the x, those are inverse functions. Alright, just sort of like addition and subtraction, or multiplication, division, square root, rate x squared, those, at the exponential and logarithmic opposites. Now, that's the case for log base 10. Oh my gosh, what about all the other bases?
You have to do the same thing.
Yeah, you'd have to go through that same process, but here's the thing. The general shape of the graph is going to be the same. This is the shape of the graph for y equals a to the x, any base. It's going to get larger and larger very, very quickly. For any base, it's the logarithmic graph is going to look, that logarithmic graph is going to look something like this, okay? It might be shifted over a little bit. You can actually, you know, shift it left, right, up, down. It might, its x-axis might be, or its x-intercept might be a little bit different based on where you're at, but it's always going to have that sort of vertical asymptote here and then slowly raising towards infinity over on the x-axis, okay? All right. So today we talked about some problems using properties of logarithms. We talked about the change of base formula, and we talked about logarithmic graphs. This should be everything that you need to know in order to take care of homework D and homework E, and that's what we'll work on tomorrow. I recommend work on that tonight. Come tomorrow with some questions. Matthew, get the button.